So we left off finishing talking about intraspecific competition. So now we're going to look at an example here. And so this is Serenade biofungicide discovered in a California peach orchard. And what we find is that they didn't have any brown rot. This disease, this fungus that would grow and was really damaging to a lot of these crops. All right. And so AgriQuest, these scientists that discovered it, manufacture it so that they can then produce it and sell it so they can use it on various crops and prevent the growth of bad stuff. Okay. And so what we see is we have this Bacillus subtilis. Okay. Is a bacteria that forms spores. Uh, and when you put it on the seeds, it's going to colonize the roots of the plants that grow. And so what we see is that this bacterium, as it starts growing on these plants, is that they're going to compete with other organisms that also want to grow on, in this case, these fruits. So this bacterium is going to compete with Rhizoctonia, Fusarium, Aspergillus, the brown rot that we see a lot in peaches. And so because of this competition, it's going to keep these fungi like brown rot from growing on these peaches. And so we've got this really nice biological control where we can protect our fruit from these fungi just by letting this bacteria grow there, which is harmless to us. This just shows that it's used on a lot of different things and prevents the growth of a lot of things. So what type of competition would this be? Well, it's between this bacteria and then lots of different types of fungi or other bacteria. So it's happening between different species. So it is interspecific competition. Okay? And what's going to happen here is this bacteria outcompetes these other fungi or whatever, and we get competitive exclusion. So we see no brown rot existing. This is nice. All right. Penicillium is produced, fungi that makes penicillin. And so what we see here is we've got these bacteria in this plate. We've got our penicillin and the penicillium producing the penicillin, and we get no growth of bacteria around this. Okay, and so what type of competition is this? Well, we've got penicillium and we've got the bacteria. They are different species, so this is interspecific as well, leading to competitive exclusion. The bacteria can't compete anywhere around this penicillium. Okay. So that was competition, our first community interaction. Okay, our second one here is predator-prey evolution. Predator-prey relationships, which can lead to coevolution, where these organisms will adapt to one another as this process occurs. Okay. And so we see different species and community act as agents of natural selection. This is often referred to as an evolutionary arms race, where only the best organisms survive, which leads to stronger individuals and so on. So if we look at this, we can talk about the example when we talked about natural selection of the fox and the rabbit. And so the fastest rabbits couldn't get caught by the fox, so they survived, reproduced. Now we got faster rabbits. Okay? But then in the foxes, only the fastest foxes are going to be able to catch those fast rabbits. And so they get food, they survive and reproduce, and now we've got faster foxes. And so this process over time builds on, and we get faster and faster rabbits and faster foxes, and then faster rabbits, and so on. And so we get this coevolution that occurs between our predator and prey. Right? So predation, right? These are organisms eating one another. And so we see various adaptations that appear because of this. So in predators, we've got legs that are built for running. Here we've got the cheetah. They've got senses, oftentimes really good eyesight, sometimes really good smell. and then camouflage so that they can ambush their prey. And this really depends on the predator and what its strategy is for catching prey. And then within our prey, we see that we have the exact same adaptations. Legs made for running, senses, they've got really good hearing and good eyesight to try and figure out if predators are nearby. They're camouflaged to be able to hide from predators. If we look at this cheetah and this antelope here, the cheetah's eyes on the front of its face, because as it's chasing down prey, it's going to focus directly in front of it. Okay? Now, this is a little bit different within our antelope or impala here, where its eyes are more on the side. And so it can get a better vision around it to try and get a better sense of where the predators are. Okay. Again, camouflage, we get all sorts of interesting things happening, right? This up top is a caterpillar that looks a lot like a stick, so it can hide from predators. This moth looks a lot like this bird drop in here. Okay. Odds are something's not going to come and eat that because it looks like poop. Then we've got our leafy sea dragons, which are going to blend in with algae. And so we get this camouflage through natural selection and evolution that protects these organisms from their predators. Okay. And here's a fawn just kind of laying still, kind of blending in with its background. Okay. And so they've got this dark brown fur and the white speckles because that should help it blend in a forest or whatever if it just stays still on the ground. Okay. Color change, snowshoe hares, weasels, Arctic fox. Okay. This seasonal change, right? This would have been natural selection. Okay. Because if they don't make these changes in the color of their fur, then during these opposite seasons, they're really going to stand out. And so when we start getting these white color in the winter, they've got much better camouflage. And then when they're brown in the summer or spring, they've got camouflage then as well. So these individuals that can change color are going to be better adapted to the environment. Okay? And so we're seeing that climate change is impacting the length of winters, the amount of snowfall we're getting in different places around the globe. What impact could this have on these populations? Well, it might not be selective anymore to have entirely white fur as you go into the winter. If places no longer get snow, then this wouldn't be a good adaptation to have. And so we could see, if things continue on and get significantly more severe than they are now, that natural selection would then reverse itself and they wouldn't have this color change anymore. Okay. We also see mimicry. Okay. In the top right image here, this is a caterpillar where the front of this caterpillar, it's got these eye spots that make it look kind of like a snake to potentially scare off any birds. We've got the anglerfish in the bottom left here with its little angle that makes it look like some little copepod, some small organism to bring fish in, and so then it can consume them. Okay. We've got two types of mimicry. We've got Mullerian mimicry. This is a warning coloration. These are dangerous species. So in Mullerian mimicry, lots of dangerous things look similar. So here we've got hornets, different types of wasps, honeybees, all have the same black and yellow patterning, and they can all sting and envenomate. Okay. Batesian mimicry, on the other hand, are when we have organisms that are dangerous, that are mimicked by organisms that are not. So in our image, we've got a coral snake, which has a highly toxic neurotoxin, which can be quite deadly. And then the mountain king snake, which is not dangerous, but they look similar. And so predators are wary of attacking the mountain king snake because it looks so similar to the coral snake. Okay. Here with Batesian mimicry, we've got the viceroy and the monarch butterfly. They look very similar. The monarch is poisonous, the viceroy not quite as poisonous, but they look similar, so birds avoid them. And that's Batesian mimicry.